Hello, and welcome to another one of my videos on the topic of management science, where we use Microsoft Excel to set up, model, and then solve simple everyday business problems. Now, if you're watching this video on YouTube, please refer to the description below the video, and in the description you will find a link to the corresponding blog post for this problem, and at the blog post you will find a written out version of this problem with full tables, and most importantly, you will find a download link for this very spreadsheet, so you can download it and follow right along with me step by step. Now, to keep the video length reasonable, I've gone ahead and built certain features into the spreadsheet. Most notably, I've gone in and selected certain cell regions and given them unique names. What I mean by that is if we go into the net flow column, which is the column of purple cells on the right hand side, if you look in the top left of our spreadsheet, it will say net flow. And that's because I have named that region of cells net flow. And that makes them easier to work with in formulas and in our solver at the end of our video. Now, I will not be going into the full background of this problem here. I'll be doing that in the next section. All we need to know at this point is that we're trying to minimize the cost of a car fund that has been given to a recent high school graduate. And that will allow him to make certain decisions on his car purchases and trade-ins over the next 4 years. And that's all we really need to know right now. Also, it is my standard practice to go ahead and draw out a diagram that represents our sort of decision tree in this problem. And when we do that, I will actually explain the background of the problem there. So let's go ahead and go into our drawing program. Let's draw out a nice explanatory diagram about this problem, and then we'll come back into Microsoft Excel, enter our data and our formulas, and we'll go ahead and solve it. So let's go ahead and set up our diagram for our fortunate student problem. Now, conveniently, I am recording this video in June of 2012, and luckily that time period fits perfectly with our problem. We're going to go ahead and assume that Connor just graduated from high school a few weeks ago, actually, and will begin his first year of college in the fall. Now, if you look at our diagram as it's set up right now, we have year 0 in the green circle, which is actually right now. And then 1 is 1 year from now, so June of 2013. And then 2 is the year after that. 3 is the year after that. And if Connor graduates from college on time, he will be graduating exactly 4 years from right now. Now let's just review what the deal is here. Upon graduating high school, Connor's parents gave him $21,000, which is very nice, of course, to purchase, maintain, and then, if he so chooses, trade in for a new car. So the total dollar amount over the 4-year period is $21,000. That's it. There is no new incoming funds. That's all he has to work with. However, his parents have given him quite a bit of flexibility. He can trade in his current car at any time for its trade-in value and then go ahead and purchase another car. Now, conceivably, he could do that every year. He could buy a car now, trade it in a year from now, drive that one for a year, trade that one in a year from that time, trade it in, etc. Now, it's unlikely he's probably going to do that because of the cost, but that is actually conceivably possible. Now, the other extreme is also possible. He could buy a car now and drive it all 4 years. And then at the end of his senior year of college, he will go ahead and sell it at its value. And then his parents are going to buy him a brand new car for college graduation. So he can buy and trade in a car as many times as he wants at any yearly interval. So that's quite a bit of flexibility. Now, if you look in the top left of our diagram, I've gone ahead and copied over the operating and maintenance cost dollar amounts, and the trade-in value at the end of each period. So a few things to note in this chart. The purchase price of any car he buys is always going to be $12,000. That's sort of the price his parents determined would be a decent, safe car. Now, as a car gets older, of course, its operating and maintenance cost goes up. So if you can see year 1, $2,000, year 2, $3,000, year 3, $4,500, and year 4, $6,500. Now that is actually a new amount each year. So by the end of year 2, Connor would spend $5,000 on operating and maintenance costs. Now the trade-in value is the value of the car after so many years. So of course, as a car gets older, its trade-in value decreases pretty rapidly. So if Connor were to trade in his car this time next year, he would receive $8,500 for it. If he waited 2 years, it would be $6,500, and so on. We're trying to balance the increasing cost of operating and maintaining a used vehicle, and then the decrease in its trade-in value over its lifetime. So that's what we're trying to balance out. And what Connor wants to do is minimize his total cost of operating and maintenance, purchasing and trading in cars over this entire 4-year period. And that's what we're going to be tasked to do in this problem. Now, the first thing I want to point out is the formula or function at the bottom of our diagram. Arc length simply represents the length of time Connor holds on to any given car. If he holds on to it for 3 years, we will have to figure out the total cost involved in that 3-year period. And that cost, or arc length, is a function of the original purchase price, which will always be $12,000, plus the operating and maintenance costs, depending on how long he held the car, and then subtracting its trade-in value at the end of that same length of time. So the total cost for an arc, or a certain length of time, will be purchase price plus operating and maintenance minus its trade-in value. So I'm going to go ahead and pause this video and start drawing in our simple arc, and that is if Connor were to hold on to any given car for only 1 year. So I've gone ahead and drawn 4 arcs, and each represents a 1-year period. So what we're looking at right here is the scenario where Connor buys a car now, a year from now he trades it in and gets a new one, a year after that he trades that one in and gets a new one, and so on and so forth through all 4 years. Now these are arcs, which means they are directional, and I'm not going to write in the arrowheads on each arc because it gets kind of messy. So I've gone ahead and put 2 green arrows, one at the top and one at the bottom, just to remind us that we're only going forward because, well, time only moves forward. So everything is moving left to right. Now that we have these 4 arcs, the question is, well, how much cost is incurred during each 1-year cycle? And we're going to figure that out by using our formula there at the bottom. Okay, so for a 1-year arc, so say 1 year, we have a purchase price of $12,000 plus an operating and maintenance expense of $2,000 minus the trade-in value a year from now, which is $8,500. And once we do all that arithmetic, we come to a value of $5,500. So for each 1-year arc on our diagram, the cost will be $5,500. So I'm going to go ahead and pause the video and draw those in. Okay, so here are our arc totals for the 1-year cycle. Now if you notice, it's $5,500 for each year over 4 years. Now if we think about that, that's going to be a problem because that is $22,000 and they've only given him $21,000. So we already know at least that this scenario is not going to work. Now, since we have our 1-year cycle cost, let's go ahead and calculate our 2-year cost. So go up here again. we have our 2-year cost. So we purchased at $12,000 again, plus our operating and maintenance cost is $5,000 because it's $2,000 for year 1 and $3,000 for year 2. So that's $5,000 minus the trade-in value, which is $6,500. Now if we add all that up, we have $17,000 minus $6,500, and that equals $10,500. So the cost of our 2-year arc is $10,500. So I'm going to go ahead and draw in those arcs, and then I'll be right back. Okay, so here are our 2-year cycles and their arc lengths, or cost. Now we only have 3 of them, from 0 to year 2 and year 2 to 4, and then from year 1 to 3. So the next thing we have to consider are our 3-year cycles. So of course that would be 0 to 3 and 1 to 4. So let's go ahead and figure out the cost on the 3-year cycle. So we have 3 years. So that's $12,000 plus $9,500 in maintenance and operating costs minus a trade-in value of $4,500. So that comes out to $17,000. So as you can see, holding on to the car for 3 years is pretty expensive because the initial cost and the operating cost is so high because of the 3-year-old car and the low trade-in value that the overall cost of this 3-year arc is substantially more than the other 2. So let's go ahead and draw in those 3-year arcs, and then we'll come back and do the last one, which is 4 years. Okay, so here is our diagram with our 3-year arcs drawn in, and those are the $17,000 arcs from year 0 to 3 and year 1 all the way to year 4. Now the last arc we have to do is our 4-year arc. And again, we have our $12,000 purchase price plus, in this case, $16,000 in operating and maintenance cost. Because remember, we're holding that same car for all 4 years. So that's quite expensive in terms of operating and maintaining it. Minus a $3,000 trade-in. Because it's quite an old car now. It would be 7 years old by this time. So we're only going to get $3,000 on the trade-in. Now this total cost comes out to, believe it or not, $25,000. So our 4-year arc is $25,000. Now we know that's not feasible, but I'm going to go ahead and draw it in real fast anyway. So this will be our entire 4-year arc with a cost of $25,000. Okay, now remember, he only has $21,000 to work with. So any path through this diagram cannot exceed $21,000. That should just make sense. And there are numerous unique paths through this diagram. We could go from 0 to 1, 1 to 4, 0 to 2, 2 to 3, and then 3 to 4, or whatever. Just by me naming a few of them, you can see that there are several different unique paths you could take through this. Now, of course, our goal is to find the path that presents the least cost. So we're going to go back into Excel, set up our problem, and then use the Excel solver add-in to find the path through this network or through this diagram that will present Connor the least overall cost. Okay, so here we are back in Excel. Now, I love drawing out diagrams to represent problems visually. It really helps us understand how our problem is going to change over time, the relationships between different parts of the problem, and things like that. So I always encourage you to go ahead and draw a diagram of any type of problem you're doing, no matter what subject area or anything like that. Okay, so let's go ahead and take a look at our spreadsheet. Now, the first thing I want to do is give you a tour of the spreadsheet and just talk very briefly about what each part's role will be. Now, if you look at the top, you will see car ownership year on the left-hand side, and then operating and maintenance cost, trade-in value, and purchase price along the top. Now, the purchase price will stay constant throughout our problem because remember that Connor's parents have decided that a 3-year-old $12,000 car is the right mix of price, reliability, and safety for him. So that will remain constant no matter how many times he trades in and buys a car. It will always be $12,000. Now the trade-in value, of course, decreases rapidly over time. So we're going to have a 3-year-old car that will then become 4, 5, 6, maybe even 7 years old, depending on when he decides to turn it in. Now operating and maintenance cost, of course, goes up rapidly as our car gets older. Now that column is not cumulative. That is actually new cost every year. So a 2-year-old car will have a maintenance cost of $5,000. So we have to keep that in mind as we're thinking about the optimum solution that minimizes Connor's total cost. Now let's go over to the right-hand side where we have nodes, net flow, and supply demand. And the supply demand column, all that is telling us is that we are, entering this process at year 0, and then we are terminating at year 4. Now the reason that year 1, 2, and 3 are 0, of course, is that none of those are where our process stops. Those are simply pass-through nodes, or in like a supply problem, we call them transshipment nodes, because we go in and out of them, but we don't stay in them. So those all have to be 0. So year 1 is a 1 because we're going to start there. Year 4 is a -1 because we are going to end there. Now, of course, the net flow is going to be the overall flow of our problem. So if we were to sum all those columns up, we better come out to 0 because that makes our problem, in the end, all even. Now, to the left of that, you see all of our different arcs we can take through the problem. So remember I mentioned that there are several arcs. Well, there they are. So you can go all the way from year 1 through year 4, and then year 1 to 2, 3, and 4, year 2 to 3 and 4, and year 3 to year 4. So those are all of our possible arcs as we move forward in time. Now the cost column is what we just did in our diagram. So all of our arcs were given costs. And if you notice, all of the 1-year arcs are $5,500, which if you remember from our diagram, that was straight across each node as we went. So year 0 to 1 is $5,500, year 1 to year 2 is $5,500, year 2 to year 3 is $5,500, and year 3 to year 4 is $5,500. So all we're doing in that column is transposing our cost arcs into our spreadsheet as they correspond with the cells on the left. Now the en route column, which is the blue column down the middle, that's actually what Excel is going to find for us. And what it's going to do, it's going to put either a 0 or a 1 in each one of those cells. Now, if it puts a 0 in that cell, that is not an arc we are going to take. If it puts a 1 in that cell, we will take that arc. So as we go through there, we could have anywhere from 1, 1 to 4 1s. It will just depend on what creates the route with the least cost. And finally, at the bottom, you will see total cost. And once Excel finds our route for us in the on route column, it will multiply over to that corresponding cost, add them together, and then put them down in the total cost box, and that will be the absolute minimum cost Connor can take on as he goes through his 4 years of car ownership and maintenance and potential trade-in cycles. Now luckily, since our spreadsheet has so many features already built into it, all we really have to do at this point is enter two formulas, then go in, open up the solver, tell it what to look for, press the solve button, and then just like that, we'll have our answer. So the first formula we're going to enter into our spreadsheet is in the top of the net flow column, which in our case is H12. So let's go up to our formula bar, and the formula goes like this. Equals sum if, open parentheses, from, comma, G12, comma, on root, close parentheses. Now, I'm not going to explain in a whole lot of detail what this does, but basically we're saying, okay, Excel, look at what's in G12. It's year 0. Now I'll go over to the from column and find where year 0 is. So in this case, it's the first 4 cells in from. Now, wherever year 0 happens in from, go over to the on route column and add up whatever Excel puts in there. And that's exactly what this part of the formula does. Now there is a second part we have to do, because this is a net flow, but it's very similar. Minus sum if, open parentheses, this time it's 2 G12, comma, on route. Close parentheses. So now we're going to ask it to do the same thing in the to column, but notice there is no year 0 in the to column. So the second half of this formula in this case will actually be 0. Now, for the other problems, that won't be the case. So hopefully, in our year 1, year 2, and year 3 cells right below this, we better have 1 minus 1, so those equal 0. Because remember, those have to be 0, because they are nodes we are passing through. But for the cell we are currently in, it will be eventually 1 minus 0 to equal 1 equals 1 in our supply-demand side. So let's go ahead and hit enter. And of course it's 0 right now because there are no values in the on route column. That's what Excel is going to provide for us. So for this column, we can just use the fill feature. So we'll just drag all the way down to year 4. If you notice, it changes them to G13, G14, G15, and G16. Now the next formula, and the last formula we have to enter, is our total cost formula. And that, of course, goes in the reddish cell at the bottom. And this formula, I've used this many times in my previous videos. We're just going to take whatever Excel finds for us in our route, which is the blue column, and we're going to multiply that by the corresponding cell in the cost column. So we will have cell in on route times a cell in cost plus the next cell in on route times the next cost plus, and so on and so forth. So we're multiplying and sort of adding at the same time 2 regions of cells, 2 cell arrays. So this formula is the sum product formula. So equals sum product, open parentheses, and this will be the on route, comma, times our cost. As you can see, it outlines each one of those cell regions in a small border, blue and green. That just tells us that we're in the right place. So we'll go ahead and hit enter, and that's it. So you can see, once we find the cost, it will give us a cost in dollars down there at the bottom, and that will be once Excel, using the solver, finds the values for on route, which we're going to do right now. So let's go ahead and go up to Data and Solver. Okay, now remember our objective is total cost. So in the objective field will be total cost. And we want to minimize total cost, so we'll select the MIN radio button. And we want Excel to change or find or manipulate, however you want to consider it, all the cells in the on route column. So this is on route. Now, we do have a constraint in this problem, so we'll go ahead and click Add under Subject to Constraint. And that is just how it appears here in the spreadsheet. We know that net flow must equal supply demand. And again, that's just because we named the purple net flow and we named the blue supply demand in our spreadsheet. So we'll go ahead and click OK. Just two things to double check. Where it says make sure unconstrained variables are non-negative, we want to make sure that is checked because we're not doing any negative, traveling through our diagram or anything. And then select solving method, we want to make sure that is simplex LP because we're using simplex linear programming. Now, if we have everything in our solver typed in correctly and spelled correctly, we'll go ahead and click solve and see if we get an answer. All right, and luckily we do. So it says solver found a solution. All constraints have been satisfied. We want to keep our solution. Yes, we do. So we'll go ahead and click OK. So let's take a look at what we found here. Now, if you look at our net flow in the purple, we will see that it is the exact same as our supply and demand over on the right-hand side. That's a constraint we told Excel it had to meet, and of course it met that constraint. Now, of course, the most interesting column is our blue column, the en route column. Now, if you notice, it's all zeros except for the two ones. What it's telling us by the ones is that that is the path, or that is the arc we need to take in order to minimize our cost. So, if you remember our diagram, we're going to be going from year 0 to year 2. And if we go down further to the bottom, then we're going to go from year 2 to year 4. And once we add up $10,500 and $10,500, that will give us a total cost of $21,000. And given our maintenance costs, given our trade-in values, and given our purchase price, that is the absolute minimum cost Connor can take on during this 4 years. And that's good because $21,000 is the exact amount his parents gave him right now at the end of his senior year. Well, that's it for this problem. Thanks for watching, and I look forward to seeing you next time.